Good morning. Myself, Dr. Maheswara Rao, Department of Civil Engineering, Institute of Aeronautical Engineering, Dundigal. So the course name is Fluid Mechanics, and the topic is pressures or forces on a vertical surface inside the water. So here, the course outcomes. So that means the student will be able to solve or define the things. So after this course outcome 1, that is CO1, so the students will be able to define the fluids and they can know the different types of fluid properties and surface tension related conditions. So course outcome 2 is the Newton's law of viscosity. The fluid classification is based on the Newton's law of viscosity. The fluids which can obey the Newton's law of viscosity are called Newtonian fluids. The fluids which are not obeying the Newton's law of viscosity, they are called non-Newtonian fluids. And related problems also they can do as per this course outcome 2. And course outcome 3 is the capillary rise or fall. So that means whenever you insert a small diameter tube in a fluid, some fluids will rise inside the small diameter pipe, which is called capillary rise. And some fluids will lower its level or fall, then it is called capillary fall. So course outcome 4 related to the surface tension. That means all the fluids at its surface, they will have the tension at the top surface. So then it is called a surface tension. And course outcome 5 is the compressibility. So compressibility means if you apply external pressure, external force onto a fluid, the fluid volume changes. That is called the compressibility. So if volume changes, those are called compressible fluids. If volume is not changing, then these are called incompressible fluids. So gases are the compressible fluids and water is the incompressible fluid. And also density. So if density is varying as application of the external load, then also it is called compressible fluids. If density is not changing, then incompressible fluids. So example for incompressible fluids are gas, and example for the incompressible fluids are water. So that is course outcome 5. The course outcome 6 is the pipe flow. So or fluid friction. So whenever fluid is flowing inside a pipe, so the surfaces of internal surface of the pipe and fluid surface, there will be frictional forces. So while traveling, so from if the fluid travels from one point to another point, so it loses the energy because of the frictional losses. So normally it is in the network of pipes in the water distribution system, it will be there. So not only one network of water distribution systems, any pipes, any fluid, as it flows, so the energies they will lose. So those are course outcome 6 related to the pipe flow or fluid friction and fluid pressure. So, and today's topic is hydrostatic pressure and forces on vertical surface. So what is the here? So if it is a liquid or water, a thin sheet, okay, and surface with thin sheet, okay. So it can be inclined position or sheet can be horizontal position or sheet can be in vertical condition. So today our class is related to the vertical surface. So this is a vertical surface. This is horizontal surface. So because it is a liquid water, so these are submerged bodies. That means which are present inside the water. So this is inclined surface. So here vertical surface we will learn today. So as per this definition, hydrostatic pressure on a vertical surface. So what is this means? is nothing but the pressure exerted by a fluid at equilibrium due to its weight. So it is nothing but the pressure exerted by the fluid. The fluid is there, it exerts some pressure on this vertical surface due to its weight. Okay. So for vertical surface submerged in a fluid, the pressure distribution varies linearly with depth. So what it is, so if depth is changing, so if the point is here, then depth is rho g h is the pressure at that point. And if depth is increased, so then pressure also will increase. So that means it is linearly variation. So pressure variation is nothing but here linearly it will vary. So as depth increases, this force, hydrostatic force or pressure is also increases. Now the formula for pressure. So the pressure formula is equal to P is equal to rho g h. So where P is the pressure at any point, rho is the density of the fluid. So kg per meter cube, or pressure is the pascals or Newton per meter square, whereas g is the acceleration due to gravity. So this is the acceleration due to gravity, 9.81 meter per second square is a constant for the earth. So then h is the depth below the fluid surface. So if the fluid is here, surface, so if you want here, then this is h. So if the point is here, this is the h. Here the density of water is constant, rho is constant, and acceleration due to gravity is also constant. These are not changing. Only the changing is the variable is the h. So that means the depth below the surface inside the water. So we'll get the pressure formula P is equal to rho g h. That means density of fluid into acceleration due to gravity into depth below the fluid surface. So if you multiply this rho g h, then you get the pressure. This is a simple problem here. So some density of water is 1000 kg per meter cube. Depth is 5 meters. That means this is the water. Its rho value is 1000 kg per meter cube. And a point, the depth of this point from the surface, this is the surface. Liquid surface or water surface. Here it is 5 meters. So depth is 5 meters. So then what is the pressure at this point? Okay, pressure at this point is nothing but the rho into g into h. So where rho is given is 1000 kg per meter cube. G is the 9.81 meter per second square and h is the 5 meters. So if you multiply this, you get the 49,050 pascals or 49,050 Newton per meter square. Then hydrostatic force. Here, till now we have discussed the pressure, hydrostatic pressure. The formula is rho g h. Whereas now we are dealing with the hydrostatic force. Okay, pressure means on a particular area, unit surface area, how much force is acting, that is called the pressure. Okay, load by area, otherwise. So here, hydrostatic force means it is nothing but a point. It is not per meter square. It is at a single point, the force will act. So hydrostatic force on a vertical surface is the force exerted by the fluid on the surface. So this is hydrostatic force is nothing but the force exerted by the fluid. So this is a fluid. This is a vertical surface. So this is a force exerted by the fluid onto the surface. Okay. It is found by integrating the pressure distribution over area of the surface. Here, if it is a regular shape, circular shape or rectangular shape, we can have length into width is the area, okay, and as a pi square by 4 like that for the circular section. So they are regular shapes. So if it is a irregular shape, so if it is a irregular shape, so how will you get the area of that particular lamina or particular surface? So that is by using the integration. So the force formula for such conditions, F is equal to integral h1 to h2 rho g h b dh, where F is the hydrostatic force in terms of newtons. it is a force F. Rho is the density of fluid as usual. G is the acceleration due to gravity, 9.81 meter per second square as usual. And H1 and H2. So what are these H1 and H2? They are nothing but the depth at the top surface. So that means till here it is a surface, vertical surface. So from liquid surface, that means water surface. This is water surface. This is vertical surface. Okay. This height, top of this vertical surface to the top surface of the liquid, which is here H1. Okay. That is depth at the top of the surface in meters. Similarly, bottom of this vertical surface. So this one is called H2. Okay. So H2 is the depth at the bottom of the surface. So B is the width of the vertical surface here. So this vertical surface height is capital H and it is having width also. Okay. So it is B. So H and B is the width and depth and width of this vertical surface. So for a rectangular surface, the height H, capital H, here is the capital H, small b is the width. Then force acting on that surface, vertical surface, is rho g h square into b by 2. Okay, rho g h square into b by 2. So here the pressure is rho g h. Okay, so rho g h square, here h is depth of the surface here, depth of the vertical surface. B is the width of the vertical surface here. So some small problem here. So for a vertical rectangular surface, height h. So that means the height is 5 meters. That is equal to h. Okay, and b is equal to 3 meters. Then force. The force formula is here. Rho g h square into b by 2. So h is the h and b related to the surface. So multiplied by the rho g. So here half is there. So h is the 5 meters square. Width of this rectangular surface is 3 meters. And rho is the density of the water, 1000 kg per meter cube. And g is the 9.81 meter per second square. If you multiply, then you will get the 3,67,875 newtons here. It is a force, not a pressure. So here another word is there, center of pressure. Okay, center of pressure means what? It is nothing but a single point where the pressure is acting, the fluid pressure is acting. So that is called a center of pressure. You see the definition here. The center of pressure is the point where the resultant hydrostatic force acts. So resultant hydrostatic force, okay, on a vertical surface. Okay, so it is not the centroid of the vertical surface. It is not the centroid. It is not the centroid of the vertical surface. It is nothing but the resultant hydrostatic force. So this center of pressure may not be equal to its centroid of the vertical surface here. So it is not necessarily the centroid of the surface and depends on the pressure distribution, how the pressure is acting on the vertical surface. Here we are getting a formula here. You can see formula for the depth of center of pressure. So depth of center of pressure is equal to IC by HC plus HC. So otherwise some textbooks we can see IG by AH bar plus H bar also. So it is nothing but the HC. HC nothing but the depth of centroid of the surface. So that means it is rectangular surface, example say. So its depth, centroid of, this is the centroid, center of gravity of this surface. That height is called here HC or H bar. Okay. So the area, this area, that means width into height. So that is called the area of that surface. I is equal to moment of inertia or second moment of area. So BDQ by 12, like that you will get the formula for that. So I IG, you can mention it as a IG or IC. So it is nothing but the moment of inertia about the centroid. Okay. So HCP is the depth of center of pressure. So you will get the depth of center of pressure HCP, or some books it is writing here H star. Okay. H star is equal to IC by HC plus HC, or HCP is equal to IG by HC plus HC. So here IC, IG one the same, H star or HCP is the same. Okay. So you can see the fluid now. So this blue color is the water fluid. Okay. So depth from the top of this is a rectangular vertical surface. This is a yellow color is vertical surface. So this is a small b, width is small b, height is the small h here. Okay. The centroid of this vertical surface to the surface of this fluid, that is the HC. Okay. HC is nothing but the distance measured from surface of the fluid to the centroid of that particular vertical surface. And IG is equal to BH cube by 12. So here the formula is B is B here, H is H small h here, BH cube by 12. We will get the moment of inertia. Okay. So depth of center of pressure is formula is I by a H bar plus H bar, where H bar is the depth of centroid of the surface. IC or IG is the moment of inertia of the centroid of the surface. A is equal to area of the surface. So A is equal to small b into small h, where moment of inertia is equal to small b small h cube by 12, BH cube by 12 here. And here HC, that is the centroid distance of the surface. So I will get the centroid of the distance HC is equal to, it is nothing but the small d, that means from here to here, then half of this portion, that means plus h by 2. So d plus h by 2 is giving the centroid distance of the vertical surface from the liquid surface. So practical considerations. So why should we learn this is vertical surface hydrostatic forces? Why should we learn? So the practical considerations here. The fluid density, one consideration. So if the fluid is denser, then the pressure also will become more. Okay. The fluid density is less. Okay. Oil is there, water is there, mercury is there. So all are fluids. So depending upon the density of that particular fluid, the pressure also or force also varies. Okay. So different fluids. So example, water, oil, etc. We have different densities affecting pressure and force calculations. So the pressure or force will depend upon the density of the fluid in which the surface is submerged. So if it is submerged in the mercury fluid, so because mercury is 13.6 centigrade is there, that means 13,600 kg per meter cube. Okay. So it is a heavier fluid, so that heavy pressure will apply onto a submerged body. If it is water or oil, so it is reducing its density so that pressure or force acting will be reduced here. And surface shape. So if the density is more, pressure is more. What about the surface shape? So shape may be rectangular, circular, or irregular. Okay. So irregular vertical surface require more complex integration to determine forces. So for normal regular shapes of circular or rectangular, so we have area formula and moment of inertia formula. So you can easily calculate the forces, hydrostatic forces. Whereas irregular shapes, you cannot use the formula. So we can go for the integration methods so that we can solve the area or moment of inertia of that particular surface, vertical surface. So if the surface is more irregular, so it will require more complex integration to determine the forces. And structural designs. So considerations to design include the total force and location of the resultant force, stability and safety. So here structural design means, example, retaining wall is there. It is a retaining wall. So what is the meaning of retaining wall? If water is staying stagnating or resting in here, so it is acting some forces. Okay. So everywhere force will be there, but what are you telling here? Total force and location. Okay. This resultant of this, all these forces will act at certain point, only at one point. So that is called resultant force. So the resultant force will act on that particular point, which is called this center of pressure also. Okay. So what is the total pressure and where it is acting? So those hence we can design the this any structures so that it can have stability and safety. So if it is exceeding the capacity of that retaining wall, so retaining wall may overturn or it may damage because of the more pressure or force applied by the fluid. And applications. So you see the retaining walls here, retaining. So what is the retaining walls? Any wall, if it retains any material, those are called retaining walls. Okay, so it is nothing but a wall. So it is normally like this. It is a wall. Okay. So if it retains water, it is a called retaining wall. If it retains a soil also, it is called as a retaining wall. So this pressure will be applied onto the wall. Okay. So design of retaining walls. If you want to design a retaining walls, we have to assess the forces on the walls and the water pressure. So how much force is acting on the wall, retaining wall, and where it is acting. So all these details, unless you know that, you cannot design the retaining wall here. Bridge piers. So bridge piers means what? So bridge is nothing but the it is a road type. So vehicles will move on the bridge. So the bridge is supported by the vertical members. Those are called piers. So these piers will be inside the water. So calculating the forces exerted by water on the piers or bridges. So how much water pressure is there onto the piers. So we have to calculate initially before going to design that. Okay. So you can design the pier sizes. Okay, circular shape or hexagonal shape, whatever it may be shape. So how much force it can tolerate. So that is called design based on the force exerted by the fluid. Okay. Tanks and silos. These also underground tanks are there, overhead tanks are there. So tank is also having wall surface. So if inside water is there, then here water force will act towards outside. Okay. So based on the fluid pressure, we have to design thickness of the tanks, wall thickness and base thickness. We have to design. So these are the applications of the hydrostatic forces. Okay. So here some small calculation here. A vertical rectangular surface H 4 meters. Okay. Width 3 meters. Okay. Submerged in water. So H1, H2. So that means this is a surface. Okay. So this is 4 meters. This is 3 meters. And H1 is top surface to top surface. That means liquid surface to top surface. H1, which is given here 2 meters. And bottom of the surface, H2 is equal to 6 meters from the liquid surface. Then average pressure is equal to rho GH here. So H means here average height. So from H1 plus H2 divided by 2. So you will get the average pressure here. Rho G H1 plus H2 by 2. So rho is the density of water, which is 1000 kg per meter cube. And G is the acceleration due to gravity, 9.81 meter per second square. And H1 is the 2 meter. And H2 is the 6 meter divided by 2. So if we do the calculation, we will get the 39,240 pascals or 39,240 Newton per meter square. So then area of surface. So this is the surface. So what is the area? 3 meters is the width, 4 meter is the height. So area is equal to 3 into 4, that is equal to 12 meters square. So if you multiply the pressure with the area, so you will get the force. Force is equal to pressure into area. Because pressure is units are Newton per meter square. Okay, it is Newton per meter square. Area is meter square. So meter square get cancelled. So then you will get the newtons, which is a force here. So force is equal to the pressure. Average pressure is 13,240 Newton per meter square. 12 is the 12 meter square area of the vertical surface. Then by calculation, you will get the 4,70,880 newtons. That much force will act onto the surface of the vertical surface. So if it is at distance of only 2 meters, so from top it is 2 meter and bottom is 6 meter. The width of the rectangle surface is 3 meters, height is 4 meters. So we are getting this much. So here it is. So if you remove this, then how much it is? So 47,000 kgs. That means 47 tons of load will act on the vertical surface. So this is a huge force. 47 tons of force is acting on a vertical surface which is having a depth of 2 meters from the liquid surface. So the top surface is 2 meters and bottom surface is 6 meters. And the dimensions are 4 meters the height of the surface, vertical surface, 3 meters the width of the vertical surface. So if you review what we learned today, okay, definition we have dealt. What is the definition here? It is nothing but the pressure or force exerted by a fluid at equilibrium due to its volume. That means the fluid is at rest. So how much force is acting by the fluid, and it is linearly varied. So as the depth is increasing, that pressure is also increases. And the formula for the pressure is P is equal to rho GH. So where rho is the density of fluid, G is the acceleration due to gravity, H is the depth below the fluid surface. And the small problem is the density is given 1000 and depth is 5 meters below the surface of the water. Then pressure will be rho GH, rho is 1000, 9.81 G, 5 is that H. So here we got 49 pascals, 1050 pascals. Then vertical surface. Okay, so if vertical surface is there, if a rectangular or regular shape, so it will be very easy. But in case of irregular shapes, okay, integration should be applied here. Okay, so it is integral H1 to H2 rho G HB into dH, where F is the hydrostatic force in newtons and rho is the density of the fluid, G is the acceleration due to gravity, and H1 is the depth of the top surface of the top of the surface, and H2 is the depth at the bottom of the surface. So B is equal to width of the vertical surface. So if it is a rectangular surface, then for height H, capital H, and width B, then the force is rho GH square B by 2. A small problem. So center of pressure. So center of pressure here it is nothing but the pressure exerted by a fluid at a particular point. Okay. So it depends upon the pressure distribution. The depth of center of pressure is given by the Ig by H bar plus H bar. So where are HC? Okay. So HC is the depth of center of pressure. Ig or Ic is the moment of inertia about the centroid, and A is the area of the surface. HC or H bar. Okay, HC or H bar. You can call it as a depth of centroid of the surface. Depth of centroid of the surface on the liquid surface. So it is a rectangular vertical surface, yellow color. So it is having width B and height H, and it is a depth of small d from the top surface, and there is depth of HC is the center of pressure. So center of pressure, centroid of this rectangular surface. How will you get the centroid of the rectangular surface? Means the small d and half of this H, because it is total H. So half of this, then you will get the centroid of that vertical surface. So centroid of the vertical surface may not be equal to center of pressure. Center of pressure is different. Center of pressure is, formula is this one. So IC by H bar plus H bar, IC by HC plus HC. Okay, HC is the depth of centroid of the surface. Surface centroid. Okay, IG is the moment of inertia about the centroid. A is the area of the surface. So practical considerations, fluid density varies, so pressure also varies. So if fluid density increases, pressure is also increases. Fluid density decreases, then pressure is also decreases. And also shape of the surface. If irregular shape, it will be easy calculations are there. If it is irregular shape, so you have to go for the integration methods. Okay, and structural designs. So whatever it may be, structures. So we have to know what is the total fluid pressure and where it is at. So those, unless you cannot design the structures, so that in order to get the stability and safety of the particular structures. So applications, retaining walls. That means any wall which retains something, which is called retaining wall. So a wall can retain the soil, or a wall can retain the water also. So here it is fluid mechanics water. So if you water is retained by means of constructing a wall, then it is a retaining wall. So how much force is acted by the fluid and where it is acting on the retaining wall, so that we can design the retaining walls. And bridge piers. So the bridge is supported by the vertical members. Those are called piers. So the piers will be inside the water in the river. So how much water is exerted onto the pier, and we have to design according to that. And tanks and silos. And if it is an underground tank, so water will be there inside the tank. So side walls, how much pressure is acting on the side walls, so that we have to calculate how much pressure is acting and where it is acting, so that we can safely design the tanks. And underground tanks or overhead tanks. So in calculation, so some rectangular vertical surface is there at a depth of 2 meters at top, and bottom of the surface is 6 meters, and the area of that vertical surface width is 3 meters, height is 4 meters, the area is 12 meters. So average pressure is rho GH, or H is the H1 plus H2 by 2. 1000 into, that means rho is 1000, G is 9.81, H1 is 2, that means top distance, and bottom distance is the 6 meters. So then once if you get this average pressure, you have to multiply the area of that vertical surface, that is small b into H, that means 3 into 4, 12 meters square. So you will get the force on the vertical surface. So references are K. Subramaniam, Theory and Applications of Fluid Mechanics, Tata McGraw-Hill's 2012, Modi, PN, and S. M. Seth, Hydraulics and Fluid Mechanics, Standard Book Course 2000. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.